So yes, you'd be aware of my lie. It was supposed to be 3, but this is definitely the that was the penultimate, number 3. This is 4. This is the final. Okay, it's long. The other one just got too long, and you don't want a long video. You'd rather chunk it, wouldn't you? So this is using and applying inverse trig functions, number 4, and we're showing through calculation of expressions into simplified answers, or in other words, solving, once we start putting a variable in there. And we'll be making, as I said in the previous video, some important generalizations which lead us to what we call definitions. Here we go. Here's example 4. Sine of inverse sine 1/3, and let y equal the given expression Let's take inverse sine of both sides, and what we have then is the following there, which essentially boils down to this level here, provided we can find a valid solution. So y equals 1/3, therefore this whole expression here should equal 1/3 if it's valid, so let's check that out. Okay, so let's again go back to this line here a second time. We are looking at basically values for inverse sine, and we're looking at elements of the domain. Okay, so it's the input for an inverse sine function. So elements of the domain. Well, from a few videos ago we know this. The elements of the domain of the inverse function is the same as the elements of the range of the original function for sine, so that's between -1 and 1 inclusive. So, and y is an element of that set. So we've got, it is true. So even though that one didn't contain any exact value type values, we saw that it ended up being justifiably straightforward, unlike the previous example, example 3 from video 3, right at the end of video 3 there. So that one, despite it being 1/3, which is not a value affiliated with our usual exact values, it still was a straightforward question. So we come to an important part now. So we've, in the last 2 examples, so this one here was example 3 from the previous video, the last example covered there, and you can see that it was a case of inverse sine of something. So that's one result we want to focus on out of 6 results. Now this is the important part, and this will actually ultimately save you a lot of work and energy, save you time. So when we've got the inverse sine of something, we have to check that the value of the variable is an element of this set here. This is what we've been doing in all such cases. Okay, so -pi on 2 to pi on 2. So here's result 1. So in general, these results follow. So if we've got the inverse sine of sine of some function or some value, let's just call it x for a general, that will equal x, provided x is an element of the set -1 to 1 inclusive. Square brackets, remember, meaning inclusive. That's an important result. So copy that down. Except I was looking at the wrong example. Sorry, example 3, what we were just looking at, weren't we? So it's actually that set there. And again, that came from what we were doing just back up here. Okay. And that will always be the case in general, provided that the value you're using is in that set. Okay. So there's result number 1. please make sure your set says negative pi on 2 up to pi on 2 inclusive of the square brackets, or you could write with inequalities like so: less than or equal to negative and positive pi on 2. Okay, either way. Note that the example we just did before was sine of inverse sine of some argument. In this case the argument was a third, and what we did, we had to test that against the set negative 1 up to 1, you might recall. So if I call the first result 1a, this would be 1b, so this is sine of inverse sine of some argument x indeed equals x, provided x is in the element of an element of the set negative 1 to 1. Okay, and you can see question 4 was an example of that, and you can see it's sine of inverse sine. So we have 1b, and it doesn't matter which notation you use there for the restriction. Okay, now here's one involving inverse cosine, and just to show you that the symbol is arbitrary, I'm going to go back and use x for this. Okay, just to show you that you don't always have to use y or x. It's a symbol. You just need to know whether it's an element of the domain or the range, and whether we're talking about a trig function or an inverse trig function. So for the inverse cos of negative root 3 on 2, we have that line, and if we take cosines of both sides, we get that. Cos x will equal negative root 3 over 2. And quick retrieval from a table of exact values, we know that cos of pi on 6 is root 3 on 2. The value of this cosine here is negative, so we're looking at not the first, we're looking at the second and the third, not the fourth. So we're looking at pi on 6 in here and pi on 6 in there. So that would mean normally that x equals 5 pi on 6 and also 7 pi on 6. Let's have a look at what x represents again. X represents elements in the range of an inverse cosine function. Okay, it's the elements in the range because it's essentially quote unquote the output of a function, and the output, the dependent variable, is all about elements in the range. And so we need to recall elements in the range for inverse cos is the same as basically the domain for cos, regular trigonometric cos, and the restriction on that was negative pi on 2 to pi on 2. Sorry, 0 to pi it is. I was thinking of sine. So from 0 to pi, we saw that 2 videos ago. So we need to check the solutions against the intervals 0 through to pi inclusive. And if you need to recall the pi part, go watch 2 videos ago or check your Cornell notes. So x must be an element of the interval 0 to pi inclusive, which excludes 7 pi on 6, and even if we take the negative 5 pi on 6, it's still not going to work. So 5 pi on 6 is the solution. So there we go, 5 pi on 6 is the solution. In other words, the answer, or the simplified solution to inverse cos of negative root 3 over 2 is 5 pi over 6. Okay, example number 6. So if we've got inverse cos of negative pi on 5, You might think, ooh, negative pi on 5, I don't come across that very much, but let's hang in there. And so let y equals the expression given. Again, use x, use y, whatever. I'm just deliberately alternating between the two of them to show you that it's the reasoning that counts. Taking cosines of both sides, so we get cos of y is cos of negative pi on 5. So let's have a look here. What are we dealing with? Y is basically to do with the range of a cosine, inverse cosine function, I should say. And so that's the same as the domain of a cosine function restriction. So we must check that y must be an element of 0 to pi. Okay, now negative pi on 5 is not an element of that set. Let's see if there's any equivalent. But cos of negative pi on 5, which is what we've got, is the same as cos of pi on 5. Okay. Both in those quadrants there, they're both positive. So it would be okay to use that. So inverse cos of negative pi on 5 is just pi on 5. Now pay attention and note that we went inverse cos of some value x. We're going to generalize again in a moment because the one we're putting up now is the other way around, deliberately so. So what if we've got a case of y equals the other way around, cos of inverse cos pi on 6. Similar question, but it's not really. Similar looking question, but it's cos first, inverse cos second. The angle is slightly different. So if you took inverse cosines of both sides, we'd get down to that level there. And we need to think about what we've got. And y is about elements of the range of a cosine function. And we have to think about the restriction. So what are the restrictions of in the domain, sorry, in the range for a cosine function? Well, it goes from -1 up to 1. So we need to check that the solution we get in a second falls between that. So I'm just going to write that down there, so it'll have to fall inside. Okay, just looking at the expression here, then we've got equating left and right. So y, that would mean, that would follow that y is pi on 6. And pi on 6 is actually an element in that set. So then you conclude in the same way we've concluded the other questions. Now, in general, these two results will follow. Based on the two examples we've just looked at, I drew attention to the other one, and this is the opposite case here. And likewise, result 2a and then 2b -1 to 1. So copy those down, they're very important results. Last part now. Trying to use the definition now more directly to speed this up, because I'm pretty sure by now you want it sped up. We've done all of this work and this thinking. So we've got the inverse sine of sine 5 pi on 6, so I've got a sketch of it there, and using the definition which we derived earlier, using result 1a, inverse sine of sine is x is just x, provided it falls between -pi on 2 and pi on 2. Well, on the face of it, it doesn't look like it does it? It's outside of the negative pi on 2 and pi on 2. Now, are there any equivalents we can use? Oh yes, there are. 5 pi on 6, sine of 5 pi on 6 and sine of pi on 6 are both positive for sine, so they're equivalent. We can use that, and lo and behold, we now have something that's in that range. So by definition, y equals pi on 6. So the solution, it is valid. So the answer to negative sine of 5 pi on 6 is just pi on 6. So that's a lot quicker if you know the definition off by heart, and all you have to say is by definition. Now, if we use the same line of thinking and consider what we've learned in the previous videos, we can also put up our two results for inverse tan and tan, the relationship there. I won't show the derivation. I'll just do a couple of examples now involving tan to finish up, but it uses all the same thinking. Just note a couple of areas of caution. Tan has to be different. There's no restriction in result 3b, any real number, and this is an exclusive. Notice the curvy brackets there. That doesn't include negative pi on 2 and pi on 2. See the previous videos. So when we confronted with these questions, now we have a choice of using reasoning, or we can just quote the definition. Okay. Now definition, result 3b. If we look at result 3b for example 9 I've just written up, well, x can be any real number. So yeah, so that's quite easy then, isn't it? So we've got y equals 2, because 2 is an element of real numbers, obviously. Or you could, if you like, if you don't want to learn the 6 definitions and quote them, if you don't do it that way, just keep using that direct reasoning that we've used over the last few videos. Either way, y equals 2. Now, what about 10 here? Can we use definition 3a? Okay, so we have inverse tan of tan x, where x is x in the restriction? No, it's not. It's outside of that, because in the positives, pi on 2 would be 6 pi on 12. So, is there a way around this using equivalence? If we think about positive values of tan, 13 pi on 12 will get us into the third quarter. So the other place where positive values for tan exist are in the first quadrant, so that would be pi on 12 also in there. So that would actually be the case that tan of 13 pi on 12 equals tan of pi on 12. Now we can use that, tan of pi on 12. There we go. So by using the definition there in 3a, we can see that, yep, the answer is pi on 12. We just had to use an equivalent and just take care. I kid you not. Here's the last one. So what if we got inverse sine of cos of pi on 3? How do we simplify that? How do we calculate it? How do we solve that? So if we let it equal y, and then we've got, if we take sines of both sides, we end up with something like this, which we haven't seen yet. So sine y equals cosine pi on 3. There are two possible ways of doing this, at least two. So we do a direct approach firstly. So let's put an asterisk there, because that's where the two different methods vary. So for method 1, we could say sine of y equals cos of pi on 3, which equals a half. Now for that, we have two solutions, y equals pi on 6, but also 5 pi on 6, because in the second quadrant signs are positive, and that will yield positive 1/2. Let's check that, but we need to look at the restriction on, now we're looking at the elements of the range for inverse sine, which is the elements of the domain for sine x, which are restricted to negative pi on 2 and pi on 2 from previous work, so therefore the solution is y equals pi on 6, so all of that equals pi on 6. Or if we go back to the step with the asterisk on it, okay, if we look at that, we could say sine of y. Now what's the relationship between cos and sine? Well, there's pi on 2 radians difference between them, so all we have to do then is to rewrite that as it's pi on 2 take the argument pi on 3. A long time ago you would have said they're 90 degrees phase difference, okay, or pi on 2 radians phase difference. So if we go pi on 2 take the pi on 3, we can write it in terms of sine, okay, and that's sine of pi on 6. Got to be able to do fractions, just have to. Sine y is sine pi on 6. And the thing is, we can write the original expression up the top there as inverse sine of sine. So inverse sine of sine pi on 6 is the same expression. That equals y. I should have said y equals. And that's definition or result 1a. Inverse sine of sine x equals x, provided between negative pi on 2 and pi on 2. And we're certainly in that domain. So the answer is pi on 6.